Hello, my dear students, and today we'll talk about Sgd algorithm and its variants in the context of machine learning applications and neural network training. And first part of our today's lecture will be dedicated to the problem formulation and its specific, which is explicitly related to the big machine learning problems, huge scale optimization. We're going to describe main notation terms such as batch size, learning rate, epoch, learning rate scheduling, and etc. Next, we're going to talk about selecting these new hyperparameters such as batch size and learning rates new in context of this specific formulation. And we're going to talk about how they affect the convergence of the algorithm, which theoretical bounds are known in this context for the convex optimization, despite the fact that original problem could be non-convex, but that's pretty usual for this area. And last, we're going to talk about different versions of Sgd, which are related to slight modification of the algorithm, such as Hermes probe, Adam, Ada delta, and etc. So all these algorithms have some quasi-Newton nature in mind, and actually they're trying to deal with the problem of selecting optimal hyperparameters to each specific problem, to each specific data set. Okay, so yes, first of all, I would like to highlight that most of today's materials are taken from dive into deep learning course, book, and site, actually, which I find one of the best way to introduce the deep learning concepts. And yes, that's it. Okay, we're gonna start with the problem formulation first. The typical problem which we are trying to solve in optimization is this. For example, let's say X from the p-dimensional Euclidean space, and we have some function f which has to be minimized. And to be more specific, we will consider this. Okay, let's say a specific kind of a function. Which is actually presented in a finite sample average form. For example, this formulation again came from machine learning, which means that if I'll consider some machine learning high-level formulation, again, that's machine learning model. It takes input data, let's say X, and it has parameters which we're going to optimize in order to model to work as we want it to work. I mean, it predicts something like Y prediction, and in the end, we want that these predictions be as close as possible as ground truth. Like, for example, right? For example, we have also, again, here we have data, and here we have Y true. And for example, if I have, let's say, n data points, we have as well n predictions and n ground truth labels. That means that you could write down MSE loss function, which is nothing else but this finite sample average. There will be I prediction of our model, which means that that's a prediction which is based on the input with the number I, and ground true I label. And we gonna minimize this mean squared error here. And actually, and usually, our loss function is a function from the parameters of the model, W, and let's write it in a more explicit form. This Y prediction depends on the W. And that's it. And why do we care about such problems, despite the fact that the formulation arises naturally in machine learning problems, is that some specifics are presented for nowadays problems, and for example, in nowadays problems we have some challenges to deal with. For example, n could be very large, as well as the number of the parameters, let's say p, could be also very large. And again, n stands for the number of data points, let's say images or text strings or something like that. And p is a number of trainable parameters of the model. Yes, and actually it means that if you want to optimize your model using gradient type algorithms like gradient descent, you will have something like this. Okay, let me write down dl, where L is this function, by dw at wk point. And as soon as our loss function is presented as a weighted sum of n functions, we can say that the gradient will be also a sum of n gradients, which means that the gradient of L with respect to W will be actually 1 divided by n, 1 over n, multiplied by a sum of these gradients. And if n is very large, it means that just calculating a single gradient could be a problem here. For example, if n, let's say 10 to the power of 7, and that's the number of points in ImageNet dataset, 10 million points. And for example, if we are talking about some like modern models for machine learning, the number of parameters could be really high. And for example, p could be billion without a problem. I mean, with a problem to train this model, but we already have such models that requires such a big number of parameters to train the model. Okay, and the problem which you have here is just calculation of a single gradient is a hard computational problem, as well as storing this gradient will be also a challenge, because if P is very big, it means that we couldn't even store the gradient, and we can even calculate like the reasonable number of parameters for some ordinary GPU with, let's say, 10 gigs of video memory, so it's gigabytes, and it means that it will be 10 to the power of giga stands for the 10 to the power of 9, right? Kilo, mega, giga, right? And also each byte stands for the 8 bits, which means that we have something like this in bits. And we know that, for example, ordinary floating point number will require 32 bits for storing one point in this format. So we can easily calculate how many floating points can we store in a 10 gigabytes video card. It will be like 10 to the power of 10 multiplied by 8 divided by 32, and we'll use the magic of fast calculations. We'll say that it will approximately equal to 10 to the power of 11, and this is something between 10 and 100. So it will be 10 to the power of 9 or 10 to the power of 10. That's the number of parameters. Then we can store, if we'll store only the vector of gradient, let's say. But actually we have to store not the vector of gradient only, but the model parameters itself, or the data, or like some stuff to operating system to work, and etc. I mean, we have a limit here. Clearly we have a limit. And for example, that's one of the reasons why we can't use something like Newton method here, because we already reach this limit in terms of the number of parameters. Because if we'll store a p squared number here, that will be insane, because we will have like a real limit as 10 to the power of 4, 10 to the power of 5. That's bad for nowadays models, and that's a challenge. And we're gonna try to solve this challenge with stochasticity. And okay, let's say how to deal with it. The idea will be, okay, guys, what if instead of the fair gradient, okay, let's say again, let's return to the original notation here, and the original notation was this. We had to minimize this sum, which is called finite sample average, over x. And as I said before, the gradient of the function, and this is actually the function, that's the function of x, and the gradient of the function is the sum of the gradients. And what if instead of the fair and full gradient computation, we're going to use some stochastic approximation of the gradient? Okay, we'll say that the gradient will be approximately equal to some vector g, and let's say if it's at point xk, the g will be at point k again, right? And the first idea here is called Sgd, and it will require only the following thing. We'll say that, okay, guys, what if the gradient will be approximated not by a full sum of all these gradients, but with only a single component in this sum. I mean that Sgk on each iteration, we're going to use just some gradient with index ik, let's say, of xk. It means that ik is chosen randomly from 1 to n. The interesting thing about such a choice will be that this stochastic approximation of the gradient will be non-biased in some specific case of randomness. For example, if I'm going to select this index ik uniformly, it means that I can just calculate mathematical expectation of such stochastic gradient, and this jk will be actually called stochastic gradient. Stochastic gradient. And this is full gradient, or just the gradient. Okay, but what's interesting again is that mathematical expectation of the stochastic gradient could be the following. We have n variants of to select this index ik, and each index is delivered with the same probability 1 over n. So I can calculate mathematical expectation. It will be this sum, the probability of selecting some specific vector and the value of this choice, and that will be this. And it is nothing else but the full gradient actually, which means that such a choice of stochastic estimation of the gradient is non-biased. That's cool. And the interesting question here is it okay to select a single summand from the whole sum that was before? Was it correct? Will it be correct enough? Will it be fair enough to select it? And actually, it's interesting that in a lot of cases, you can use such an idea, and this was proposed in the middle of the previous century, and that's what was called originally Sgd, stochastic gradient descent. And if you'll compare the convergence of this algorithm with the original gradient descent in terms of the number of iterations. Okay, what does it mean? That's the number of iterations. That's the function value. For gradient descent for some nice function, let's say strongly convex function, you'll have something, or just convex function. Okay, that doesn't matter here. You'll have something like this under some assumptions on the gradient, on the step size selection, but there are cases when the algorithm will converge, so we'll consider those cases. But what about the stochastic gradient? Will it be faster? Will it be slower? And it's obvious that in terms of the number of iteration, it could be significantly slower than the original algorithm. It means that it will be something like this, and we even lose the monotonous property because now we have a direction of not the full gradient, but its stochastic approximation that can be not a descent direction in some cases. Okay, that's something like Sgd, and that is Gd. But what's the reason to use this algorithm is that if you consider the same evolution, but not on the number of iterations, but for example, on the oracle calls or just computational time, let's say. That could be interesting because, yes, on each iteration of Sgd, like you'll probably decrease the function value not as good as in full gradient algorithm, but each iteration of Sgd will be n times cheaper than the original algorithm. So we have a trade-off here, and in different cases, like with different scenarios, the situation could vary slightly, but now we can expect something like this. I mean, we can expect something like, okay, Sgd is now faster than the gradient algorithm, but that's a trade-off. Actually, that's not guaranteed anywhere here, but that's the illustration of the idea that Sgd iteration is n times cheaper, which could be significant because, as we said before, n could be 10 to the power of 9, for example, or 10 to the power of 8. That's ridiculous, or like that's very big. That's it. Again, that's the gradient descent, that's the stochastic gradient descent. And the stochastic gradient descent algorithm will be formulating as follows. And still we have a problem of step size selection, which is called learning rate in these algorithms. But that's a common problem for gradient-based algorithms. Okay. It's interesting idea here is to introduce the concept of mini batch or just the batch. And again, let's take a look at the initial problem. Initially, we have a gradient which is the sum of a very big number of gradients, which is n. But in a stochastic gradient descent, we have the estimation of such average value using only a single term. The natural question here could be, okay guys, why do we need to use only single term to estimate this average value? What if we'll take, let's say, several terms and average it? We will be closer to the original solution. And the obvious answer is yes, and you know that that's the question of statistics and probability, in fact, and you know that the empirical mean will converge to the actual mean, to the ground truth mean, with the number of samples increasing, right? That's pretty obvious, and that's where was introduced concept of mini batch Sgd. And here we have the stochastic gradients presented in the following way. It will be 1 over b and some ik from 1 to b and the gradient of function ik of xk. So again, let's take a look and let's compare these formulations. And we can see that we just replace the number of n by the number of b, which is called mini batch here. So b here stands for the batch size. And the whole bunch of gradients will be called a batch, or the whole bunch of selected data points will be called as batch. That's not very important here. And still, the formal algorithm will be formulated as follows. Okay, let's do it this way. That's it. Again, the idea is to estimate finite sample using not a single term from the sum, but some subset of the initial sum, which is significantly less in terms of the number of summands, which means that B is significantly less than the original number n. And actually, like obviously, we'll receive acceleration for n over b times for the calculation of the stochastic gradient here. But in fact, we can accelerate even more because each of the batch term could be calculated in parallel, which means that actually if all our batch gradients are fit into the GPU memory, we'll have the same time complexity here as for the previous variant, which is called Sgd, which means that parallelization gives us like a free lunch here. By free lunch, I mean in terms of time which is spent to calculate the stochastic gradient. Okay. That's it, and that's a formulation of these algorithms, and we'll have an interesting discussion on what is batch here, what is batch here, what is epoch, and how to select them. Okay, let's describe the idea of the epoch term here. And suppose you have a data set which is presented as a matrix and which has n rows, and each row here stands for the data point, and this data point could be of, let's say, size n. That doesn't matter for us. And I'll say that I'll select a batch size which is equal to 2, which means that I'll randomly select on the first iteration of mini batch Sgd, for example, this point from the dataset, and let's say this point of the dataset. And they all go to the first iteration of Sgd. Next, I'll select some other random rows from the initial matrix, and actually that's an interesting question about should we consider selection with or without replacement, because that's a little bit different scenarios in terms of the fair like theoretical bounds. But in fact, we're treating the probability of selecting each row as 1 over n, which stands for the selection with replacement. But typically, it's implemented in another way where we have to select only those of rows which are left here, which means that the scheme with without replacement, because that's that could be, that could bring us more information about the original data and allows us not to miss any data point, but analysis for the scheme with replacement is a little bit simpler. Okay, so for the next batch, I'll select, let's say, this row and this row, for example. That will be the second batch. For example, for the third one, I'll select this and this. That will be the third. And at the next step, I'll pretend that I have one more data point here for convenience, but these questions are actually solved in the practical implementations of the frameworks such as PyTorch, JAX, and TensorFlow. And let's say green. Okay, now I just run through all the data I have here. Okay, and the number of mini batch Sgd iterations after those you're seeing all the data in the data set is called epoch. I mean that these 4 iterations are called epoch. But after we finish with these 4 iterations, we'll actually go to the next 4 iterations and next and next and next and etc. And that's just a question of notation. And in fact, the term epoch is not really like connected to the inner nature of the algorithm. That's just a convenient notation to present in like reports and papers, because that's one of the notation. That's it. Because what matters here is the number of iterations, obviously. Okay, so we have an epoch here, we have a batch, right? That's the number of iterations. And in fact, how many iterations of mini batch as Sgd, mini batch Sgd equals to 1 epoch? That's a pretty obvious question here, and it will be n over b, right? For example, here I had 8 points in my data set and batch size, which is equal to 2. That means that the total number of Sgd iterations, mini batch Sgd iterations in one epoch is 4. Okay, that's pretty like understandable, but the question here is, okay, guys, now we have more hyperparameters than it was before. We still have the learning crate selection problem, but also we have a batch size hyperparameter, which is also needed to be tuned somehow. And that's actually a very interesting question. And let's discuss on how the batch size affect the training, especially in neural network training or like machine learning training. Okay, we have 2 possible options here. 2 extreme options. When the batch size is equal to 1, and in this case, stochastic gradient will become something like that. It will be just ik from xk, and that's actually Sgd iteration, which was discussed before the mini batch Sgd version. But also we can have another extreme option here, where the batch size is equal to the number of points in the data set. In this case, our stochastic gradient will become a full gradient or vanilla gradient. And it will become just ordinary gradient descent, which is often called vanilla gradient descent here in this context. Vanilla. And how these two options are compared to each other, that's interesting. And the straightforward answer for the question is the less, the lower value of B I'll choose, the higher the variance of stochastic gradient I'll have. That's understandable, I suppose, because if you'll select the whole sum and the batch, which is equal to n, you'll have zero variance because you'll have no stochasticity at all. But the most noisy case will be with the b equals to 1. That's the minimum value of b you can choose here. And how does the noise in the gradient affect the training? That's a very important question in nowadays machine learning problems, and I cannot give some final answer because it's still an open question, but some intuition could be provided here. And in this intuition, actually noise plays an important role in optimization. Noise and gradient, I mean. And we'll consider this idea first about non-convex setting, because it's interesting that a lot of practical machine learning problems in fact are non-convex problems, but we're still using convex optimization to solve them, and often that's the only way we can perform here, but it works unexpectedly well. I mean, let's consider some illustration here. I mean, what if your function will be some tricky non-convex function? Let's say something like this. That's very bad function. And suppose that your gradient algorithm was started somewhere, let's say here. If you use vanilla gradient descent or just gradient descent here, you'll for sure, with the correct step size, go to the nearest, sorry, not the nearest, but I mean that this minimum could be closer to the original point than, for example, this minimum, but you'll just go descending to the nearest stop point, which will be a minimum here. So you'll just finish here without any doubts if you'll select step size correctly. That's the Sgd point. And as you can see, in a non-convex setting, that's not the best option to stop because that's just a local minimum. But if you'll have some noise in the gradient, you can skip actually initializing at the very same point as it was discussed before. You can actually skip these local minima. For example, if the noise is very high, your algorithm could oscillate in a very huge manner here, something like that. It could go here, 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 and etc. But if the noise level is reasonable in some sense, that's very hard question how to determine this reasonable level of noise. But still, for example, for this function, if your noise level is reasonable, you can, for example, okay, go here, go there, and just go there, and finish somewhere at the wide local minima. I mean, let's say here. That's like artificial example, but still the intuition behind it could be useful. And the intuition could be again like this, for example, Sgd trajectory will be something like this, but Sgd trajectory could be something like, okay, go here, and then here, and then here, 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 here. It also could be worse, like the final minimum could be worse than in gradient descent. For example, it could have gone somewhere here, for example, and here, and this minimum is worse than the previous one, but it could be in opposite way, right? And the intuition behind it is that one of the, like initially, we're gonna use, we were using stochastic gradient instead of the full gradient computation because of the memory issues and time issues, right? But in fact, the noise in the gradient has regularization properties in terms of escaping some local minimum. And let's state it clearly that noise in the gradient could help us to deal with non-convexity. That's a very general statement, and sometimes it's very strong statement, but here, like, sometimes it could help us, sometimes not, and that's strongly depends on the noise level. But the, I mean, the absence of noise, the zero noise will lead you just for the nearest local minimum without any options here. But the stochastic gradient provides some hope to escape bad local minimum. And in fact, as I said before, this is important in machine learning, and that's why selecting batch size which is equal to n maybe not a good option in non-convex problems, because you'll just go to the nearest local minimum. That's just as it expected, I mean, right? That's it. But what about overall complexity here? And let's consider some theoretical results about convergence of stochastic gradient descent algorithm. Convergence of stochastic gradient descent algorithm. And actually, nowadays, we're calling mini batch Sgd as just Sgd. That's a little like confusion here, but as far as we are using parallelization to compute all gradients in a batch in parallel, we spend the same time for the mini batch Sgd as for the original vanilla Sgd, right, with the unit batch size. And we are referring to this algorithm as just Sgd. That's not very important here. Okay, convergence of Sgd. And let's take a look at some known results. For example, here's the result for the strongly convex function and mu here stands for the strong convexity constant, alpha here stands for the learning rate, for the step size, and B here actually stands for the bound of the gradient norm. I mean that the squared gradient norm, and to be fair, that the maximum value of mean value of expected value of expectation of the squared absolute value of the gradient is b squared. So, like, to be short, it's just the level of the gradient, some constant b. It could be treated as a Lipschitz constant for the function, in fact. And what's interesting here is, yes, and R stands for the initial distance from x0 to the optimal point in the problem. So that's just like radius of the problem, right? We're starting somewhere far from the solution, and the R reflects this distance from the initial point to the solution. And what's interesting here is if this term 1 minus 2 alpha k mu less than 1, then we'll have linear convergence of expectation of our trajectory here, and it means that that's true for the only first term, but not the second. This term will go to 0 as k tends to infinity, but this term will not change at all. I mean that b is a constant here, mu is a constant for a given function, and alpha, if you'll consider a constant step size formulation, that's also a constant. And it means that, in fact, for the stochastic gradient descent, we do not have convergence if we'll not decay the learning rate here. It means that it converges somewhere near optimum point, but you have some radius of stochasticity where your final value will oscillate here. Let's consider some illustration of this. That's the vanilla gradient descent on a squared function on a plane, right? And we have the situation which is quite familiar to us. The algorithm just go orthogonal to the level lines and go directly to the optimum. But what if we'll simulate stochastic gradient descent algorithm here by adding some noise to the original gradient? Let's take a look here. That's the calculation of the fair gradient, and that's some noise addition with zero mean level. And we're just going here at the anti-gradient direction with step eta t. But eta stands for the constant learning rate here. Let's verify it, because yes, LR is constant learning rate. And we'll receive this type of convergence. And again, the minimum here will be at 0, 0. Somewhere here. And in fact, if you'll tend the number of iterations to infinity, or I mean increase the number of iterations, you will not receive a convergence. You will receive some like oscillations in such a stochasticity ball, right? And what's interesting here is that the radius of this ball could be described in a strongly convex case here as this second term, and it this radius is strongly depending on the learning rate or on the step size, as well as for example, it's depending on the mu and the b, but the mu and the b are the function characteristics and typically couldn't be changed. That's like oracle response here. But the alpha is a hyperparameter, and if you'll decrease the alpha, we can expect this stochasticity ball radius decreasing. That's interesting. That's probably one of the most important theoretical suggestion about stochastic gradient convergence here. And let's and for these reasons, people are often use learning rate schedulers here, and that means that our learning rate is not constant, but some decaying function, for example, piecewise constant or exponential or polynomial here. And the problem with the learning rate scheduler is that you'll never know in advance how far should you start to decrease the learning rate value. That's a problem, but in fact, that's interesting. For example, if you consider stochastic gradient algorithm with the exponential learning rate decay, you'll receive something like a convergence here. Again, we have something like this and something like this. In fact, it means that the algorithm stopped a little bit earlier than it should. I hope, right? Is it correct? Yes, and in fact, we have to play by ourselves a little bit here, and let me switch to the interactive notebook here. Okay, that's the interactive notebook here. What's interesting is if you'll consider higher number of step size, you'll receive this this cloud of points and this oscillation, which was described before. And for example, if you'll decrease a learning rate initially, here, for example, eta stands for the learning rate, increase it twice, and we'll see that this cloud of points becomes a little bit smaller. And if you decrease it more, like 10 times comparing to the original level, and for example, increase the number of steps 10 times, you'll still receive this cloud, but the radius of this and the variance, I mean, of oscillations are quite smaller than in the original setting. And that clearly corresponds with the error bounds which were described above, for example, this. And let's consider more steps here in exponential learning rate decay setting, and we can still hear that we didn't reach the minimum, which is somewhere here, and that's probably of the very aggressive learning rate decay. We can improve it by setting the constant of learning rate decay a little bit more slight, and that's it. We can see that starting from the learning rate of 1, which is a great learning rate, comparing to the let's say 1/10, we're decreasing it step by step, and for such a big amount of iterations, we don't have here any big cloud of points because the learning rate decreased to almost 0 value here. And it's the same situation for the polynomial learning rate scheduler. And for example, for polynomial learning rate, it can be a little bit slighter than little bit more slight than the exponential, because exponential is very aggressive decaying, in fact. That's also a hyperparameter. That's also a problem that's gonna be addressed, but still it's very interesting here to see the idea. And that's the primary reason of using step learning rate schedulers. And typically, like in modern machine learning tasks, people often use learning rate decaying at some point of training procedure. Okay, let me highlight that at the notebook there could be found a brief convergence proofs for the convex case, and for the strongly convex case can be found on our site fmin.xyz. That's it. For example, methods, first order methods, stochastic gradient descent, and these are the proofs. And let me switch to the idea of a parallelization first, and how we can speed up our computation. For example, that's the case of computing matrix multiplication here, and our goal initially to compute the matrix A, which is a product of matrices B and C. And to compute ij element of matrix A, you have to take row I from the matrix B and column C from the matrix C and column J from the matrix C, and like multiply it. And if you make it in a cycles way, for example, here is random matrices B and C, and let's calculate it in this way and take a look at the time. You'll have to place each time, like you're calculating the element, you'll have to place I row of B and J column of C in the memory and out of the memory. That's why this method is very slow in terms of the computational time. But if you do it in a parallel way, that's the way you can compute, for example, the whole column of matrix A. You'll just take the matrix B and you'll multiply it by iteratively by each column of matrix C, right? That strategy lead you to the very significant speed up because you can see that you are not doing this obsolete stuff of taking in the memory or taking out the memory the same information. But ideally, you can put all the matrices like once and just multiply it in a parallel way, and you'll do the best here. But it's not always the case when you can fit both matrices into the memory, and in this case you're gonna split the matrices into blocks and do the same idea of parallelization, but on a smaller matrices. That's how it could be done, and that's actually how it's done in like efficient libraries implementation, like the Torch again, JAX, etc. Let's again run it. There was some problem. Yes, that's it. So in terms of flops measuring, we have this difference, like almost like 700 times faster than element-wise computation. And that's why actually mini-batches are so efficient here, because again, computation of each term in the full gradient could be done independently and those in parallel. That's why it's very efficient. And we can even pose the following question: what will happen if I'll increase the batch time, the batch size with the epoch training time? you can ask yourself this question again. You'll have an epoch, you'll have a batch size, and if you'll increase the batch size, the epoch training time will increase, decrease, or will not change at all. And the interesting answer here will be that if your batch fits the GPU memory, the correct answer is that your epoch time will be decreased. So you'll increase the complexity, but you'll decrease the overall time. Why so? Because the number of iterations in a single epoch will be smaller, because if you have, for example, 1000 points in the data set, and firstly have batch size which is equal to 10, and it requires 100 Sgd steps, and in the second case you have batch size which is equal to 100, and it requires 10 Sgd steps. But Sgd steps with different batch size are almost the same in terms of time complexity, because all these things are computed in a parallel. But the number of iterations is smaller. That's why epoch time could be smaller if all this fits to your memory. And we can even demonstrate it on some specific machine learning example of predicting the noise aircraft with respect to different parameters. That's NACE data set. That's not very important for us, the specific machine learning problem, but let's compare this training of Sgd algorithm with learning rate equals to 1, batch size equals to 1500. That's very great. That's almost equal to, that's actually a total number of examples. That means that that's just gradient descent here, no stochasticity at all, and 10 epochs. And you can see how fast it is. And for example, if you'll consider a smallest possible batch size here, which is equal to 1, we'll receive significant time spending increasing, and you can see it right here, because here you just calculate all terms in the stochastic gradient at once, but here you have to do it in a sequential way. That's why this training is much faster. When you increase the batch size, you'll decrease the total training time, in fact. But that's not always the case when your batch could fit the memory. In a modern language modeling problems, people use dozens and even hundreds of graphic cards to deal with the batch size and the huge size of the data. And the interesting graph here is that's comparison of loss function value evolution and time spent on the process. And purple line here stands for the Sgd, which refers to the unit batch size, and blue line stands here for the full gradient descent or vanilla gradient descent. And in fact, if you increase the batch size, you'll go somewhere from the purple line to the blue line. And you can see this dependence is not monotonic, because if you'll set the batch size which is equal to 100, you'll clearly win in terms of the time spent on training, because again, each iteration is significantly cheaper than the gradient descent, but still, that's the trade-off between complexity and number of iterations, right? And this trade-off is very interesting. Here again, from purple wine, you're evolutioning first to the batch size which is equal to 10, then to the batch size equal to 100, and at the end you'll go to full gradient descent, which is here. That's interesting, and that's always a trade-off between the batch size and between the complexity of one iteration and total number of iterations. And let's talk a little bit about how to speed up this training, and we'll switch to the handwriting here. Okay, we still have two open questions about selecting main hyperparameters for the stochastic gradient descent here. The first one is how to select the batch size. And how to select the learning rate, or it would be correct to write a batch size, right? Because it's not specific. And as we saw before, the batch size stands for the noise level, and those can be considered as some regularization technique which lead to the better generalization in some cases. So that's why actually we know some drawbacks of using high, very high batch size, and not high, very like big batch size, and very small batch size. That's very noisy, and that's probably very very long in terms of the training time. And that's an active area of research so far. That means that there are several works that advocates some specific choice of the batch size, but I can sum it up to some short recommendation here. And the overall recommendation will be the following. Now it can change a little bit. Now recommendation, select B as big as it can fit the GPU memory, but it shouldn't be equal to n. I mean, it's better to write it shouldn't be close or like approximately n. B still should be significantly less than n, because if B is like half of n, that's a problem, because the noise is too small and you lose the regularization property of stochastic gradient descent algorithm. But typically for the modern problems, people are trying to use very large batches, because it's like speeding up the training, and that's important for large models here. How about the learning rate selection, and what's the correct answer to this problem? And we'll try to solve this problem by using some adaptive step size selection strategies. So, let me write down the answer in advance, and later we'll talk about it. So, for prototypes, use adaptive algorithms with default hyperparameters. but for the like production tasks or for the actual tasks, for the, let's say, final usage, it could be better to use Sgd plus momentum. We'll describe what is momentum a little bit later, with hyperparameters tuning and learning rate scheduling. Or schedulers. That's it. So what about adaptive algorithms and momentum? Let's talk about it a little bit. The momentum is a very important concept in numerical optimization because it's like a free lunch, almost a free lunch here. So you'll probably always have to use a momentum idea. And what's going on here? Suppose we have a quadratic function which is very ill-conditioned, which means that the condition number of the initial matrix is very high, and the behavior of the gradient algorithms will become a zigzag behavior with such a problem. And imagine that instead of going to the anti-gradient direction, you're going to the linear combination of anti-gradient and weighted sum of previous direction. And here you can see that if you sum the first step with the second step, with the third step, with the fourth step, and etc., you'll receive something which is pointing out to the minimum. And that's interesting, and that's pretty common in such problems. That's like stabilization here. And again, what we are doing formally is this. We're going not to the anti-gradient direction, but to the direction of vector v, which is a linear combination of previous direction taken with some scalar beta and current anti-gradient, or g could be a gradient actually. And in fact, if you explicitly write it from the last term to the very first term, you'll receive nothing else but this weighted sum of all previous directions. So that's called actually exponential weighted moving average, because if beta is smaller than 1, that's the correct choice here, then beta squared is less than beta, and beta cube is less than beta squared. It means that you're looking for the current antigradient, but you're also taking care about the previous directions. And the far the direction, the less it takes part in your like new moving direction of optimization. And that's actually what is called Pollack momentum, which is also called as heavy ball method or just momentum. And that was developed actually also in in the previous century, and that's one of the provable way to accelerate stochastic gradient descent or just gradient descent. That's a very useful idea. And for example, here, if you'll consider the same problem of ill-conditioned quadratic function with 1/2 learning rate as a constant step size here, and you'll see this behavior. That's not a convergence, that's bad. But if you'll use a momentum here, again, what's going on? Instead of going through just J vector here, G vector, you're taking an exponential average or just multiplying the previous direction on beta and current gradient. So you're going to the anti-gradient and some combination of previous directions. So it means that you're stabilizing the thing here. And for example, if the beta hyperparameter is here close to 1, it means that you're taking in your consideration all previous step without any decaying here. That could be not good, but yeah, that's it. But if you set beta to the 0, you'll just immediately forget all previous information you accumulated here. For example, here we have the same behavior as it was before, right? Because if you just don't use any previous information, that's just a gradient descent scheme. But if you sum, let's say 0.5 point, you'll have a stabilization effect and acceleration actually. In fact, you can use even more, even higher value of eta here. And for example, if here I would use the same value of eta, I'll just have a divergence. But when I have momentum, that's stabilization, that's acceleration, and that's important. And again, typically we're using stochastic gradient descent with the momentum. But that's the theoretical analysis, we'll skip it for now. Adaptive algorithms were developed to address the problem of learning rate selection procedure. And for example, in other grad algorithm, we could use something like an adaptive learning rate here. For example, if J is a stochastic gradient vector, then you'll just update vector S, which is nothing else but the sum of squared historical gradients here. And it means that here, each coordinate has its own learning rate because all operations here are element-wise. That's the element-wise square operation, squaring operation, that's element-wise summation, and that's element-wise dividing here and taking square root. And you can just forget about this plus epsilon here because it's presented here only for like avoiding division by 0. Epsilon is a very small constant here. For example, epsilon here is 1e minus 6. That means that you can just skip it. And again, what do we have? For weights updating, we're using anti-gradient, but learning rate is adapted using some historical information which was accumulated in this vector S. Okay, vector S, here is the square root of this vector. So here you have just the square root of all the gradient information, which means that if in some coordinate the gradient was very high, then you'll have to go a little bit more careful in this direction. Like the idea was this, because it can help you to avoid divergence, because in divergence your gradient like either increasing or staying the same but very big, right? Because if your gradient is very small, then your it should be close to an optimum here. But the obvious problem with such a algorithm is that in such a formulation we can only decrease the learning rate, because this S is always increasing during our optimization process. And it means that denominator of our fraction here is always increasing, and the total fraction value will decrease through the optimization procedure. That's a problem. That's why we can use not just summation, but weighted summation here. The same idea was applied to the momentum, right? We can just use multiplication of previous value of S and the same idea for the new squared gradient here. And here, your S vector will not always increasing. It can decrease if, for example, somewhere in your procedure there was some big gradient, okay, it was, but then the gradient will become smaller and the S value will also become smaller just because of this gamma multiplication here. Gamma is less than 1 actually. In fact, that's a different gammas here, and that's different. Let's say here, yes, that's like different convergence. That's called term as prop. That's one more like idea to address the problem of selecting learning rate. Let's select it adaptively. And there are actually a bunch of algorithms to deal with. For example, one can say, okay, guys, we can use the exponential weighting for S updating, but also we can take a look at the gradient normalization, rescaling some. Again, you can just skip this plus epsilon here and take a look at the clear version here. And for example, Adam, which is pretty well known just for the like nice name and nice convergence properties for some default tasks, but not necessary for your task, is again using these two historical vector v and s, which means that you have to store two more additional vectors in addition, right, to your original stochastic gradient vector, which increase the memory demands here. And you'll just, okay, guys, we just go through the direction of weighted, historical weighted, exponentially weighted gradient vector and divided by S vector, which is again a sum of squared gradients, which was weighted in an exponential manner here. That's it. Again, a lot of different algorithms here presented, and you can check the idea here. They're on the notebook. That's very interesting, and that leads us to the final conclusions about the methods and hyperparameter selection here. And in fact, yeah, that's me. In fact, again, the practical suggestions will be to use any adaptive methods and for your prototyping. But if you need some like production model training or finding the best value of like the best parameters for your model, it's probably better to use Sgd with momentum, because very often state-of-the-art results were obtained using this algorithm and proper hyperparameters tuning procedure. So you have to like spend a lot of time here trying to figure out which specific parameters are the best. And for example, that's a short demo of different adaptive algorithms here. Let me click here, and for example, that's a non-convex function with two minimas here, and that's like an evolution. And we can see here Adam, Sgd, momentum, Hermes prop. For example, here clearly adaptive algorithms converge to the one minima, while Sgd and momentum converge to the closest one. And interesting that I hope, and I mean that this minima is smaller in terms of the function value than this. And here only Adams, for example, go for it, despite the fact that it's far from the original starting point. But that's, again, that's a question of your specific problem, because it can be vary depending on which problem you are trying to solve. But momentum, as we said before, is like free lunch in terms of acceleration, almost free lunch, because you always have to store momentum vector. But yeah, that's it. Thank you for your attention, and enjoy your noise in the gradient.